Okay, yeah.
Okay, all right. Well, join for dinner tonight.
Small world.
Catch up. Okay, so we'll get started. So just a reminder that this is the second to last colloquium. There's one more next week, and then we'll be done for the semester. So this week we're pleased to have Nicole Arulanatham visiting from the Space Telescope Science Institute, where she's a Draconi Fellow. And Nicole got her bachelor's at UCLA, her master's at Wesleyan, and her PhD at University of Colorado at Boulder. She's worked on young stars, protoplanetary disks, planet formation, and a bunch of interesting surveys with names like ULLYSES, Odysseus, Penelope, and MIDAS, apparently. So I'm gonna assume she's gonna tell us more about that. And she tells me she's a long distance runner, and she's actually gotten more into it since she's been in Baltimore, not necessarily in Boulder. So interesting to hear about the running community in Baltimore as well. So today she's telling us about constraining the chemistry of planet formation in the era of HST and JWST. And please, Nicole, take it away.
Thank you. Thank you all for having me here. I was telling someone earlier, it's been great to be back on a big football campus. The East Coast has too much lacrosse and I don't know how to play, so it's a bit rough. So today we're going to talk a lot about HST and JWST and UV and infrared spectroscopy. And I wanted to start the talk by showing off this beautiful cosmic galaxy egg, which is on display at the American Visionary Arts Museum out in Baltimore. And it's something that's really cool about having STSCI in Baltimore is that there is a very big arts community in Baltimore. There are a ton of artists who are influenced to make space-based art. And the Cosmic Galaxy Egg is one such piece. And the author, Andrew Logan, said that he was influenced by seeing the Hubble Deep Field. And so you can kind of walk all the way around the egg and see these really beautiful little details. So if you ever have a chance to visit Baltimore, you should definitely come check out EVAM. So I'll start the talk by giving an introduction to star and planet formation, and I'll tell you about how we can use HST and JWST to answer some of the big open questions in the field. And specifically, I'll be talking about work that we're doing using data from the Hubble UV Legacy Library of Young Stars as Essential Standards, or ULLYSES. There's a nice little ship logo here. And I'll also talk about what work that we're starting to do with JWST that will also answer some of these same questions. And finally, I'll leave you with some conclusions and future directions. Now I know we're getting close to the end of the semester and it's after Thanksgiving, so I've tried to put the main point of each slide at the top of the slide. So if you feel lost at any point for any reason, just feel free to read off that sentence at the top of the slide and you'll be caught up. And I'll try to pause for questions at a few places throughout the talk as well, just to keep us awake. So I love getting to give an introduction to planet formation because I get to show off this beautiful graphic that was made by the Office of Public Outreach at Space Telescope. And so you'll notice that the temperatures are in Fahrenheit for the public to more easily understand very cold and very hot. And I'll try to put these back in Kelvin for you. So the process of forming planets and stars start with these very giant molecular clouds. And the composition of these clouds are typically 100 times more gas than dust, and there will be a little bit of ice thrown in too. And these clouds will be very cold, so somewhere between 10 and 20 Kelvin. And if the cloud is perturbed, it will start to gravitationally collapse, and this is what starts the process of star and planet formation. So our cloud will collapse, and at the very center, it will get very, very hot. And that 5 million Fahrenheit temperature is about 3 times 10 to the 6 Kelvin. And so that's right around the temperature that we need for hydrogen fusion to start in the stellar core. And while this star in the center is heating up, all the rest of this material is either accreting onto it, or it's forming an accretion disk around the star, which is what we're seeing in this kind of middle picture here. And eventually the last of the stellar envelope will have fallen onto the star or onto the disk. And we will start to actually be able to see the star through all of this planet forming gas and dust and ice. Now, there are a lot of people in your department who are studying the various stages of planet formation, in the earlier stages, but I focus on this last stage where we can actually see the star and start to get a sense of how the stars influence the disk.
Did you make these graphics?
No. So these were made by the Office of Public Outreach.
They're beautiful.
They're gorgeous. Yeah, they employ a lot of graphic designers, and so they make all of these graphics in consultation with the scientists who do the work. And so one of my collaborators, actually, Joel Green, was the contact scientist for this graphic. Yeah, so if you ever need any graphics for a talk, check out the STSCI website. Okay, so my area of focus are these systems where you can see the star, but you can also still see this disk of planet-forming material. So within the disk, there will be, and this is a very simplified version, but there will be a lot of collisions between the solid material. And when these solid grains stick together, they'll slowly grow into larger and larger planetesimals, and eventually you'll form a much larger planetary core. That planetary core will eventually start to accrete gas, and eventually you'll end up with a beautiful exoplanet exclamation mark. So when we look at this graphic, we see this really nice uniform process, right? You start with your cloud condenses, you have a disk, you make your planets, and boom, you're done, right? But when we look at the observed population of exoplanets, it immediately becomes obvious that this process is not uniform at all. So to date, there are about 5,500 confirmed planets around other stars. Most of them are Neptune-like. Then we have a bunch of other gas giants. We have super Earths, we have small rocky worlds, and we have a population of planets that's just classified as unknown. So these are systems where we don't really know what the mass of the planet is. And you'll notice that these demographics are very different from what we see in our own solar system. For example, we don't have any super Earths. We don't have any mini Neptunes. We do have rocky planets and gas giants, but there's a whole lot of other things around other stars that we don't see here and that we don't really know how to make just yet. And you'll notice that this is just about the types of planets that we can detect, right? This says nothing about the compositions, nothing about their atmospheres, their cores, anything. So it's clearly a very complicated process. And I think that's very well reflected by this graphic from Karin Oberg's recent review paper. Now, how many of you are looking at this and feeling deeply overwhelmed? Yes, that is exactly why I wanted to show this slide. So we're not going to talk about all of these processes, but each text label here marks out a physical process within the disk that controls the chemistry within the planet-forming disk. And so we see our star here at the center, and we have these kind of black curves that are tracing the flared protoplanetary disk. Yeah.
Hopefully this is not a point you're going to make very soon, but on the previous slide, is that just because of observation bias that we see that kind of distribution?
It's part of it. It's much easier to detect the giant planets. So a lot of the planets that we've detected, the exoplanet scientists have detected so far have been discovered using either the transit method, where you're seeing a dip in light as the planet passes in front of the star, or by the radial velocity method, where you can see the perturbations that the planet is causing in the host star spectrum. And so those signatures are much easier to see for giant planets than with the smaller rocky planets.
Do you think that this ratio outside of observational bias has merit? Like, does this physically also match what ratios you would expect to see outside of observation?
That's a very good question. There are some other people who have done some really rigorous statistical analyses on these. I can send you the papers actually after the talk. Yeah, but that's a really great question. Yeah. So we can look at this diagram and we can see all of these processes that work together to produce planets. And it can be wildly overwhelming. And so for my purposes, I'm focusing on what's going on in this very middle region. So I'm thinking about the host stars themselves and the impact that the host stars will have on the gas, dust, and ice that's very close to them. So this is inside of about 10 to 30 AU, mostly inside of even about 5 AU. So where rocky planets are found in our solar system and poking out to where we're starting to see the gas giants. Now, young stars create a very dynamic, energetic environment within the protoplanetary disks. And this is illustrated very nicely by this cartoon from a 2016 review paper by Lee Hartman. So we have our young star at the center here, and these red lines represent magnetic field lines. And young stars are known for being very heavy accretors. And so when we observe them, we can see signatures of material that's traveling along the magnetic field lines and falling onto the star. We also see disk winds and jets that are being driven away. So this is material that's being driven away from the system, typically by the star itself, that's producing a lot of X-ray and extreme ultraviolet photons that heat the gas and send it away from the star. And then we also see very close to the star an inner gas disk and very warm dust. And this is material that's warm enough that we can observe it with the instruments on board JWST. And so this is kind of where I focus. So I pay attention to what the star is doing to the gas and the dust in the very inner regions of the disk. Now, this accretion process, where material is flowing along the magnetic field lines and falling onto the stars, produces a lot of excess radiation at ultraviolet wavelengths. And this ultraviolet radiation is what sets the temperature structure of the planet-forming material. And so here we're looking at a cut from a model of a protoplanetary disk. And so the height above the disk midplane is on the y-axis, and the radial distance from the star is on the x-axis. And we're basically looking at a 2D slice of this disk here. And we're looking at the temperature distribution across the disk. So the redder regions are where the temperature is hotter, so between 500 and 2000 Kelvin. And the bluer purple regions are where the temperature is cooler. So this is where the UV photons aren't really able to get into the disk to heat the gas, but we can see this very nice layer of red here where that radiation is reaching the gas and controlling the chemistry within that gas layer. So now with JWST, we are able to observe the composition of that gas layer. And to jump ahead a little bit, this is a beautiful spectrum from the mid-infrared instrument on board JWST that was taken by one of the teams with guaranteed time on the telescope. So we're looking at the flux density on the y-axis and the wavelength in microns on the x-axis. And we can see emission from atomic hydrogen that's falling onto the star. So this is hydrogen that's actively being accreted. We can also see emission lines from neon-2, and this is typically coming from the jets that are being driven out from the star. We can also see carbon dioxide, which is within the disk itself, and we can see emission from silicate dust grains within the disk as well. And so this is pretty revolutionary that we're able to see all of these signatures of the planet-forming environment in a single spectrum from JWST. At the same time, yeah.
So there are a lot of lines on there. How many of those are identified?
So a lot of these are actually water lines. A lot of them. And when you pull all of the, I don't know how many of you have ever taken a look at the HYTRAN database, but it's a very nice library of molecular transition data. And if you pull all of the emission lines out of the HYTRAN database and stack them on top of the MIRI spectra, you'll see that a lot of those wiggles in the spectra line up exactly with where we see transitions of water. And so this has been, a lot of work was done to remove any fringing effects from the data. And so all of these wiggles are very real, at least within this wavelength region. So it's actually to the point where you have to subtract the water before you can get any of the other science out of the spectrum because the water is in the way, which is a pretty wild thing to have happened. So we're at this pretty amazing time where we can see all of these molecules in the disks. And the people who study exoplanet atmospheres are starting to see the same transitions of those molecules in the exoplanet atmospheres. And so here we're looking at the transmission spectrum of an exoplanet. And we can see this nice bump where carbon dioxide is absorbed by the planet's atmosphere as it passes in front of the star. So we can see carbon dioxide in a protoplanetary disk. We can see carbon dioxide in exoplanet atmospheres. And we have absolutely no idea how to get from point A to point B. And so what we think we can do is really nail down the initial conditions of the planet formation process by looking at these protoplanetary disks, and then send all of those initial conditions off to the people who do planetary evolution models to run their simulations and try to reproduce what we're seeing in the exoplanet atmospheres. So this is all very complicated, but in this era of HST and JWST, we are very uniquely positioned to be able to characterize the high energy radiation that's coming from the stars and the composition of the stuff that's in the planet forming disks with JWST. So before I go on to the next part of the talk, I wanted to pause for questions. Yeah.
On the previous slide, your spectrum for the disk, is that generalized? Is that something that we see across the board? No matter where we look at these protoplanetary disks, we see water everywhere?
So this is something that we're just starting to see with JWST in the larger sample. So a lot of the disks have a ton of water, and then there are some unusual ones that don't show any water, but instead show higher abundances of carbon-bearing species. And this is something that we think might be linked to the stellar spectral type. And at least that's what early observations with Spitzer indicated, but we're not quite sure yet. We're just kind of in the early stages of figuring out what's going on with JWST. And we have much more sensitivity with JWST than we did with Spitzer, so we can observe much larger samples and we have much better spectral resolution as well. Any other questions?
Speaking of the spectrum, so it has this sort of trapezoid feature in it. What's that? Between say 8 and 10 microns? Is that a thing?
So this is what we think is a very, very diluted silicate emission feature. I don't know if I believe it's that wide. So the detector gap is somewhere in here, around 9 microns. And so I think there is maybe some stitching that's gone a little bit funny there. But 10 microns is right around where we would expect to see emission from silicate grains. And the flatness of the bump basically tells us something about the properties of the grains. And so if it's real, there might be some interesting information to come out of there. And you can see another little bump in the spectrum over here under where it says forsterite, which is also a dust emission feature. I don't think it's actually that wide, but there probably is a bump there.
Cool, got it, thanks.
Yeah.
I have more of a general question. If let's suppose I change the spectral type from a B to a O or from a G, how are these graphs supposed to change according to that?
That is an excellent question, and that is exactly what I am currently actively trying to understand. So I will say a lot of the targets that I'll be talking about for the rest of the talk are much smaller than those types of stars. They're typically K and M type stars. The hotter stars, their disks disappear very quickly, and so it's much harder to capture them in the active forming planets. Yeah. All right, so we can go ahead. So, led very nicely into the next part of the talk. So based on observations of planet-forming disks with Spitzer, we think that stars with stronger UV radiation fields should have a less rich molecular chemistry happening in their protoplanetary disks. And so I'm showing some snapshots from some models that were done by Catherine Walsh. And she basically modeled the disks around different types of stars. So on the left panel here, we're looking at the HCN distribution around in a disk around an M-type star. In the middle, we're looking at the same thing, but around T Tauri star. So this is the solar mass young star. And on the far right, we're looking at the distribution of HCN molecules in a disk around a Herbig star, which is about a 2 solar mass young star. So we're looking at 0.5 solar masses, 1 solar mass in the middle, and 2 solar masses on the far right. And what Catherine's model showed was that since the M dwarf disk is expected to receive less energy from its host star, the HCN molecule should be able to survive for longer. Whereas in the more massive disk, or in the disk around the more massive star, more radiation is being generated, and that will destroy more of the molecules in the disk. And sure enough, with Spitzer, we don't see very many molecules in these disks around the slightly more massive stars. Now, to run these models, it's very typical to use an integrated UV flux. And so the models by Catherine Walsh were really novel in that they used an entire spectrum to go into the models instead of just a single UV flux. And so here we're looking at the UV flux density on the y-axis and the wavelength in angstroms on the x-axis. And this bottom dashed line is the UV field that was used to represent the M-dwarf spectrum. In the middle, we have the spectrum that was used to represent the solar mass T-Tauri star. And at the top, we have the spectrum that was used to represent the slightly more massive Herbig star. And to approximate the Lyman alpha emission from atomic hydrogen, a simple Gaussian was used, and it was scaled to a value that represents about 88% of the total UV flux from the star, because that's what we thought at the time that the Lyman alpha would do. And when we look at the observed UV fluxes and we look at the Spitzer luminosities, we do see some trends. So on the left-hand side here, we're looking at the luminosity from CN molecules observed with ALMA on the y-axis and the UV flux on the x-axis. And on the right-hand side, we're looking at the luminosity of HCN molecules observed with Spitzer and the total UV flux on the x-axis. And so if we look at the HCN first, we can see that the disks that were receiving more UV radiation actually had more HCN, which is the opposite of what the models predicted, right? We thought that if you put more UV into the disk, you would destroy all your HCN molecules. And if you were destroying your HCN, then you would be left with a hydrogen atom and a CN molecule. So we thought you should have more CN molecules if you pumped more UV radiation into your disk. And instead we saw the opposite, where there was a decline in the CN luminosity going out to higher far UV luminosities. And so when we include the actual UV observations and compare these to the molecular gas distributions, we see something that's very different from what we initially expected to see. And some of this is due to just small number statistics, right? Like these are not very large samples. And unfortunately with Spitzer, we didn't have the best spectral resolution. And so it's very difficult then to model the emission lines that we see from the HCN and actually get reliable constraints on the abundances. And so it's very likely that on the right-hand side, what we're seeing is a temperature effect, that when you put more UV radiation into the disk, you're just heating up the molecules and making them emit more, as opposed to actually producing more molecules. Yes.
Wouldn't you also want to normalize the line luminosity against another common molecule, say, you know, CO or H2 or something?
Yeah, so there's some complications with that. For the sub-millimeter flux, we could definitely normalize it against CO. And the plan for some of the JWST observations is to use the rho vibrational or the 4.7 micron CO emission to normalize the molecular gas abundances. But unfortunately, with the Spitzer samples as well, we didn't necessarily have uniform infrared observations to be able to normalize them. And the problem with these disks is that we could have used 12 CO to normalize it, but the 12 CO is very optically thick. And so that would have added some more problems to the analysis. But you'll notice that on the x-axis here, the FUV fluxes are normalized by the total UV luminosity. So it also turns out that the observed UV spectra from young stars are much more complicated than a simple black body. So this is an example of a UV spectrum from a T-Tauri star called Gia Auriga. And you can see immediately that while it sort of looks black body-esque, there's certainly a lot more features in the spectrum that may be very important for setting the temperature structure of the disk. You'll notice that down here, the spectrum is much noisier, and this is just a sensitivity issue. So a lot of these disks are very faint, or sorry, a lot of these stars are very faint in the UV. And so as you go down to shorter wavelengths, your spectrum starts to get into the noise limit of the detector. But we see lots of atomic emission lines from silicon-4, carbon-4, helium-2. There's another carbon-2 up here, and then there's H-alpha in the red at the top. And so approximating the UV spectrum as a black body in models may not be giving us quite the right picture. And so that may be one reason why we're seeing different things in the data than what we would expect from the models. And so I mentioned that we were having a problem with small number statistics. And I was very fortunate that at the time that I was getting ready to finish up my PhD in Colorado, STSCI approved the largest director's discretionary program ever to be executed on Hubble. And this is called ULLYSES, the Hubble UV Legacy Library of Young Stars as Essential Standards. Now, ULLYSES is a director's discretionary program, and so this means that all of the data is publicly available, and anybody can download the spectra and use them for their research with no problems. And you'll be able to ask people on the ULLYSES implementation team for help if you have any trouble with the data reduction or anything. So it's really a wonderful tool. Now, the ULLYSES program was given a total of about 1,000 orbits of HST time, which is enormous. It was really spectacular. And about 500 of those orbits were used to observe K and M type T-Tauri stars. And so we got observations of 71 additional K and M type T-Tauri stars. And so this is in addition to the 30 to 40 that we had in the archive prior to this. So you're almost tripling the sample size. The new targets span 9 different galactic star forming regions. And so we're able now to look at the impact of star formation environment on the disk compositions. And there were also 4 targets that were selected as monitoring targets. And so these were given multi-epoch observations. They were studied 3 times per stellar rotation period for 3 different stellar rotation periods. And so this is a data set that we can use to look for flares and basically to do time domain spectroscopy with young stars. And again, all of the data are publicly available at the ULLYSES website. So if you're interested in using the data for your own science or just in having a look, you can definitely go and download it. And these are just a few of the papers that have been published with this data from the low mass star side of the community so far. Yeah.
So maybe you'll cover this later, but is it, in terms of data products, was the focus mostly on spectra or on images or?
Spectra, yeah. So I'm going to show you some images later, but it turns out that these, in the UV, these systems, for the most part, are very, very faint, which makes it really hard to do any kind of imaging. You want something really bright to spread the photons out into an image. And unfortunately, that's not the case for a lot of these targets. And so it's a set of 1D spectra from the cosmic origin spectrograph and from the Space Telescope imaging spectrograph. But you get wavelength coverage from about 1,000 angstroms all the way out to 7,500 angstroms. So it goes from the far ultraviolet through the near ultraviolet and into the optical.
I guess one issue is that this capability might be going away, at least for a long time.
Exactly, yes, yeah, so.
What is it with the UV you mean?
If the UV
Because of COSs?
Yeah, unfortunately, you know, it feels like every other month now there's a notification that Hubble had an anomaly and had to stop science operations, and the instruments won't necessarily last forever. And so it's quite possible that we're going to be going without space-based UV capabilities until the 2050s, when the next Habitable Worlds Observatory launches. And so it's been really critical to establish this UV library now before this capability goes away. And these observations are also quite difficult to obtain. It takes a lot of observing time, and it's challenging. So this was really an amazing data set, and there's a ton of work to be done in analyzing all of the stuff that's coming out of it. Now, and I'll just mention this quickly, in addition to the ULLYSES program, Carlo Manara at ESO was able to get a large complementary program on the VLT to acquire near UV through near IR spectra for all of the ULLYSES targets using the X-shooter spectrograph on the VLT and also Espresso and UViz. And so there's this beautiful data set now that's going from the far UV all the way out to the near infrared. And this, the papers down on the right there are just a subset of the work that's been done with this Penelope data set. So in keeping with the theme of ULLYSES, right, we have the Odysseus collaboration that's analyzing the ULLYSES data, and then the Penelope collaboration that's looking at this ground-based data from the VLT. So my main area of focus in looking at the ULLYSES spectra has been thinking about Lyman alpha. Now, Lyman alpha emission is everywhere in the universe because it's produced by hydrogen atoms, and there's atomic hydrogen everywhere. And for a long time, we thought that the hydrogen Lyman alpha emission lines from T-Tauri stars should look like this. So you should, in theory, start with a nice Gaussian line profile. And then, because these protoplanetary disk systems have hydrogen that's flowing out of them, we think that the left side, the blue sides of the emission line profile should be absorbed. So it's a simple Doppler effect that the material moving towards us along the line of sight will absorb the blue shifted photons. And you'll notice this big blue bar, and that is unfortunately air glow. So I mentioned that these systems are very faint. And so unfortunately, we're able to observe them with the cosmic origin spectrograph because it doesn't have a slit. So it has a very wide entrance aperture, and this allows contamination from Earth's atmosphere to enter the slit. But thankfully, we know what velocities that's found at, and so we can just mask it out. And you'll notice that this Lyman alpha emission is incredibly broad, right? It's going out as far as about 900 kilometers per second in either direction. And this is much broader than we would expect from a typical emission line. And again, this is a property of Lyman alpha. So because there's so much hydrogen in these systems, the Lyman alpha can actually scatter and make the profile wider. And I'll show you a nice demonstration of that in a minute. But we thought that all of the Lyman alpha emission lines from T-Tauri stars should look like this. But actually, when we look at the full ULLYSES sample, and if we measure all of the flux on the red side of the emission line and all the flux on the blue side of the emission line and take the ratio, we see this enormous spread. So this line here is marking where there's the same amount of red and blue Lyman alpha. And so all of the profiles that we think we should see are for the targets that sit above this dashed line. And then there's this whole population of targets that actually have more blue than red Lyman alpha, which is super weird and also really interesting. And so on the x-axis here, sorry, these are each of the targets in the ULLYSES sample up to data release 3 at the time. And so we can see this spread in 2 orders of magnitude, sorry, 3 orders of magnitude in the shape of these Lyman alpha emission lines. So I mentioned scattering, and I'm going to show you this movie here. And we're going to watch the movie a couple of times and look for 2 different things. And so this is an animation of Lyman alpha scattering that's by my colleague Max Kronke, who does extragalactic Lyman alpha radiative transfer. And on both the y and x axes, we're looking at distance from your source of Lyman alpha photons in the middle. And so if you watch this line wiggle around, you'll notice that our test photon is getting bounced all over the place in space, right? It's moving from one end of the box to the other. It's taking a very funny path. And so this is what we would expect from a random walk pattern. So our photon is just getting bumped all over the place in space. Now, the second thing I want you to notice is that the color of this line is changing. So it started out as red, then it changed to blue, then it changed back to red. The reason it does this is because as Lyman alpha photons scatter, they can actually change in frequency to try and escape the hydrogen medium at a lower optical depth than what you would see at line center. Yeah.
Do you consider the rotation speed of the gas in this Lyman alpha photon simulation?
So not in this one, but I'm going to show you something where we did. Yeah, this is a very simple approximation here. Yeah, so we can see that the Lyman alpha photons are scattering both in space and in frequency. And the way that Max describes it, I think this is a really beautiful analogy, is that if you have a room and you lock your Lyman alpha photon in a room and it's trying to get out through the wall, but the wall's really thick, and then all of a sudden a window appears, the Lyman alpha photon is going to scoot to the left and it's going to go out the window. And so that's basically what's happening in frequency space, is at line center, you have so many hydrogen atoms that your photon can't escape. But if it scoots to the left in frequency space, then it becomes more optically thin and your photon can get out. So I want to pause here for a second, because I know that was a lot of radiative transfer that I just threw at you. Does anybody have any questions? Yeah.
Well, when it comes to, I mean, it's a pretty analogy, but I mean, like, what about the medium is requiring a Lyman alpha photon to escape, aside from abundance? Because like, it just doesn't, you know, maybe I just not paid attention enough in my radius transfer class, but it doesn't really make sense to me intuitively that if like a photon will like need to escape like a dense medium of hydrogen, for example.
Yeah, so it can also just be absorbed and stay there.
Okay, yeah.
Right, there's nothing stopping it from doing that. But when you have a source of radiation, your photons are going to come out of it, and your flux at some distance from that source is going to go as 1/r², right? So it's a natural part of radiative transfer for those photons to diffuse in space. But when you have a ton of stuff that might absorb those photons, the process gets more complicated. And what specifically is happening here is resonance scattering, where and what this means is that your hydrogen atoms have produced a lot of Lyman alpha, but now your Lyman alpha source is surrounded by a ton of other hydrogen.
Mm-hmm.
And so that hydrogen can just very easily absorb the Lyman alpha and re-emit it, right? Because the energy has to go somewhere.
Mm-hmm.
And so the hydrogen can very easily absorb the Lyman alpha, have a slight frequency shift, and then re-emit it. Whereas if you were putting this, and I'll talk about this a little bit, if you were putting this Lyman alpha into molecular gas, different things can happen to that molecular gas. It can get pumped up into excited electronic states. It can be photodissociated. The energy is going into different processes, where with hydrogen specifically, because it's hydrogen that produced the Lyman alpha, it will do this scattering process where it just absorbs and re-emits the Lyman alpha. Does that kind of make a little more sense?
Yeah, that does actually. Thank you.
I think my question might be out of the scope of this talk, but I'll ask it anyways. How does the photon know the distance away from the window? Is there a set distance before it no longer is able to find the window? Like, is it a spectrum of window distances that it could theoretically jump to?
That is a very good question. It does not have any reason to know where the window is. It's just kind of going to carry on, right? But it'll basically just bounce around in space until it finds something that's less optically thick where it can escape. And I shouldn't personify the photon. I think that's probably where the confusion is coming from.
I guess my specific question was, is there a range of possibilities for the distance away from the window? Is it a set, like stratified, the photon can shift by this much and still escape? Because I've never taken a radiative transfer class, so I have no idea.
Yeah. So the photon will treat each independent. So the scattering events are independent, right? And so the photon will just scatter, and then it won't remember where it was before, and then it'll scatter again, right? And so where the window is depends on the property of the hydrogen medium that it's escaping through. Mm-hmm. And so what people are interested in the extragalactic context is basically mapping the structure of hydrogen gas in between galaxies and how the Lyman alpha scatters through that. For us, we're interested in tracing how the Lyman alpha is scattering through the protoplanetary environment. Yeah, so it's a very good question.
Thank you.
But all of these questions are really good for demonstrating, right, that this is an extremely complicated problem. And so when I was showing some of these Lyman alpha emission lines from T Tauri stars to some of the people at Space Telescope who do extragalactic radiative transfer, all of them were asking, well, why aren't you including scattering? And our answer was, well, we have a ton of other stuff to worry about, right? If you think back to that cartoon from the beginning of the talk with all of the physical processes that influence protoplanetary disk chemistry, that's a lot of stuff. So you can imagine that if you stick all of those physical processes on a grid, then you add a ton of chemical reactions to try and reproduce the chemistry, and then you add millions of Lyman alpha scattering events, your code is going to be running forever. Even if you're here with access to some of the best computing resources in the world, your code is going to run forever. And so we wanted to tackle this problem very simply at first. And so we used my collaborators' very simple shell models as a start. And so here we're approximating our hydrogen medium as just this little circle surrounding a source of Lyman alpha. And our model parameters are just the velocity of that little shell, whether it's moving away from the source of Lyman alpha or if it's moving towards it. And then we also thought about the abundance of hydrogen in the shell, the width of the emission coming from the Lyman alpha source, and the turbulence or the temperature within the medium. So this is a very, very, very simple approach, but one that's very easily applied to a large sample like the ULLYSES program so that we can start to pull out some trends and get a sense of what's going on with those Lyman alpha emission lines. And so we fit these shell models to all of the targets in the ULLYSES program. And these are the relationships that we found between the shapes of the Lyman alpha profiles and the model parameters. So we can start over here on the left. So on the y-axis in all three of these panels, we're looking at the ratio of red to blue Lyman alpha flux. And on the x-axis here, we're looking at the velocity of that hydrogen shell. And this is the area where we found the biggest correlation between the shape of the Lyman alpha profiles and the velocity of the shell. And so we can see that these targets with positive hydrogen velocities, so this means that the shell is in the shell model framework, this means that the shell is moving towards the source of Lyman alpha. We find that these are the targets that have more blue than red emission, and the opposite is true for the targets in the top quadrant there. And when we compare the shapes of the Lyman alpha profiles to the column densities of hydrogen and the widths of the Lyman alpha profiles, we don't really see much correlation. So it's very clear here that the velocity of that outflowing or infalling H1 is what's setting the shape of the Lyman alpha profile. Yeah.
Just another question, like how do you get the NH1? Like, is there some conversion factor that you just use, or?
Yeah, so that's a free parameter in the
model.
model.
Okay.
Yeah. Yeah, and so we know how far in distance the photons have scattered, and so we can just calculate a column density from there.
Okay.
Yeah. And so if we compare these H1 velocities that we've derived from the shell models to other properties of the protoplanetary disks, we actually find two distinct categories that seem to be showing us an evolutionary sequence in Lyman alpha emission. So our targets that look like what we expect, with much more red Lyman alpha than blue emission, tend to have much more full protoplanetary dust disks. So they don't have any signs of gaps or cavities. They have very strong signatures of jets and disk winds. And so what we think is happening is that the Lyman alpha photons are scattering through the outflowing H1. And this is what's setting the shape of the profile. Now for the opposite scenario, where we're seeing systems with more blue than red Lyman alpha, these tend to be in disks that have a lot of dust substructure. So we might see big gaps in cavities that are carved out in the planet-forming material. We don't see any signatures of jets on these targets, which is very interesting. But we do see signatures of perhaps photoevaporative winds that are driven by the radiation from the central star. And so these systems are also still accreting, and we think what's happening is that the Lyman alpha is only scattering through those accretion flows from that cartoon that I showed you earlier, and not scattering through any of the disk winds before reaching the observer. And I'll talk a little bit more about the implications later in the talk. But this was very unusual. It looks as though the Lyman alpha radiation field is evolving as the disk itself is evolving. And this may have some important implications for the chemistry that we'll explore.
Is there any correlation with the orientation of the source?
There is not. That was the first thing that we thought might be the case, that if the disk inclination was more edge on, then we would not see any of the scattering that's coming through the wind. But that does not seem to be the case.
Yeah. Do you have like ALMA for all of these?
Not for all of them. So Karina Malko, who is a postdoc at ESO, just had an ALMA program approved to fill in the rest of the ULLYSES sample. So there's a subset of them that have ALMA observations, and her program will hopefully slowly over time start to fill in the rest.
Great.
So that'll be really awesome for exploring the substructure and exploring the disk inclinations and a lot more of the geometry.
Mm-hmm.
Yeah. So I will say all of this came from looking at the 1D spectra that came from the ULLYSES program. Wouldn't it be just lovely if we could actually spatially resolve the distributions of Lyman alpha across the disk and actually see where those photons are going instead of just guessing from the 1D spectra? Well, it turns out that as I was starting to ask this question, it turns out that a postdoc long before me had asked the same question. and had gotten a successful HST program through to observe spatially resolved Lyman alpha in a protoplanetary disk. And then he ended up leaving the field to become a birder, which sounds really wonderful. But this data set was collected in 2011 and had just been sitting in the archive for a while. And while I'm not a theorist, I was very fascinated in looking at the observations. Now, while COS on HST is not able to spatially resolve these systems, the Space Telescope Imaging Spectrograph is. But unfortunately, the Space Telescope Imaging Spectrograph is not quite as sensitive, and so it can really only image the brightest, most nearby disks. And so in this top plot, I just wanted to show a little finder of what we're looking at. So these are observations of the face-on protoplanetary disk around TW Hiya. It's about 50 parsecs away. And this is a beautiful ALMA image from Jane Wong's 2018 paper. And so the STIS observations, which were taken actually before the ALMA observations were done, took one slit across the center of the disk, shown in the solid white line there. And then the program also acquired offset spectra in either direction. So the dotted lines show where the spectra were taken plus or minus 0.2 arc seconds from the center of the disk, and then plus or minus 0.4 arc seconds from the center of the disk. Yeah.
Does this mean you're restricted to looking at disks that are face on?
So we are not. For this purpose, we thought that we would best be able to see the Lyman alpha scattering across the disk if we did look at something that was face on. But I'm going to show you what we found from these simulations, and actually we can probably learn a lot more if we look at the edge on disks too. Yeah, that's a very good question. So this bottom image is our spectrum that was taken from the center of the disk. And so on the y-axis here, we're looking at the distance along the slit. So in that horizontal direction at the top. And in the bottom, we're looking at velocity space along the emission line. So the Lyman alpha line center is here, and we can see that that's completely absorbed. There's so much hydrogen that we're not getting any photons through. But as we go out to longer wavelengths, we start to see the broad wings of those emission lines start to pop out. So that's exactly what we were seeing in the 1D spectrum.
What's the red line?
The red line is marking off line center. Oh no, sorry, the red line is marking off where the surface brightness peaks. And then line center is this white dashed line here. Yeah. So now, when we step off the disk to plus 0.2 arc seconds on the bottom and minus 0.2 arc seconds on the top, you'll notice right away that this surface brightness profile has diffused a little bit spatially, which is exactly what we would expect if the Lyman alpha photons are scattering through the system. We expect that profile to gradually spread out in space. And when we go out to 0.4 arc seconds, we see that the profile has spread out even further. And so this was the first observational evidence that we had of these Lyman alpha photons diffusing in space across a protoplanetary disk. And at an offset of 0.4 arc seconds at the distance to TW Hiya, that's corresponding to about 50 AU. Now, a big part of this effort was trying to model the spatially distributed Lyman alpha photons so that we could explain with models what was happening. And so my collaborator, Suk-Jun Chung, who is an MPA, has a very sophisticated Lyman alpha scattering model. And this is something that he's able to use to capture the rotation of the disk and capture Lyman alpha scattering in a rotating disk. And so he ran these radiative transfer models. And this is an edge-on view of the model surface brightness profile that he got. So we're looking at the height above the disk midplane on the y-axis and the radial distance along the x-axis. And he noticed that when we only looked at the Lyman alpha scattering from the protoplanetary disk, there wasn't enough brightness in the model to actually reproduce what we observed with STIS. And it turns out that TW Hiya also has a protoplanetary wind. And so this is an image of that wind that was taken with the MUSE spectrograph on the VLT. And we can see in oxygen 1, this beautiful face-on wind. We're looking right down the barrel of the wind. And so when Sukjun included the wind in his radiative transfer models, that seemed to fix the problem. So on the right-hand side here, we're looking at the normalized surface brightness on the y-axis and the radial distance on the x-axis. And the data from STIS is shown in these black points. And if we only use the disk, you basically have to make the disk enormous to be able to reproduce the data, and we know that that's not true. But if you include the wind, then you can add the wind to the disk, and you begin to actually reproduce what we were seeing with the observations at positions far from the central star. But the problem here is that we're looking at a wind in a face-on disk, right? I don't know if anybody would have known that this was a wind, right, if I hadn't told you that it was. And unfortunately, this is where it would be very helpful to be able to look at edge-on systems. And so how are we going to get better constraints on these disk wind geometries? The answer, surprisingly, turned out to be with JWST. So this final collaboration that I'm going to show you quickly is called Mapping Inclined Disk Astrochemical Signatures, or MIDAS. And this was a Cycle 1 General Observer Program on JWST that was designed by Melissa McClure at Leiden University. And the goal of this program was to look at edge-on disks in order to explore the composition of the ices in the planet-forming midplane. And so this beautiful edge-on disk was selected as a target. This white contour here shows where the sub-millimeter dust continuum is. And then we see these two beautiful nebulae that were observed with HST. And so this is scattered light from the top and bottom surface of the disk. And the other reason to choose this disk is that when it was observed with Spitzer, it showed beautiful ice absorption lines. So we're looking at the flux density on the y-axis here and the wavelength in microns on the x-axis. And there was this beautiful absorption from water ice. There were some silicate features, there were some ice blends, and there were some gas emission lines, but that wasn't so interesting. We don't really care about that, right? If we can see the ice absorption features with Spitzer, then it's going to be a slam dunk with the more sensitive instruments on JWST. And so in flipping through the spectral cube that came down from the mid-infrared instrument on JWST, this is what we saw. Now, the disk itself is along here, so that white contour that we saw in the previous image would be right here. And instead of just seeing that disk, we saw a lot of spatially extended emission at wavelengths corresponding to transitions of molecular and atomic gas. So the red here is tracing emission from molecular hydrogen at 17 microns. And the cyan contours are tracing emission from ionized neon. And if we remove the kind of central disk from this image, what we're left with is this beautiful X shape that has an opening angle of about 70 degrees on either side. And this is about what we would expect if this was an MHD wind. And so we can take those wind opening angles, we can stick them into Lyman alpha radiative transfer models, and we can get a much more accurate picture of what is happening with the propagation of UV radiation through the disk. Now, the winds, of course, have very interesting implications in their own right? This is a way that we can trace mass loss from the system, and these mass loss rates tell us the upper limit on the timescales for planet formation. And so when we can do this in a much larger sample with JWST, we can really constrain the timescales for planet formation. But it's also interesting in terms of being able to trace the UV radiation. So I will leave you with a few conclusions. The ULLYSES spectra provide really nice estimates of the radiation environment, particularly where we see rocky planets in our own solar system. And so we can nail down the temperature structure of the disks using those UV radiation fields, and then we can observe the warm molecular gas in those regions with JWST. We found actually that Lyman alpha photons can travel much further from the star than the rest of the UV photons. And this is something that can impact chemistry in cold gas that we're hoping to start observing with ALMA. And finally, it is very, very difficult to include real UV spectra in physical chemical models. And so we can use the ULLYSES spectra to give us some guidelines from where to start, and we can slowly add complexity to our models from there. And finally, I just wanted to leave you again with a reminder that Baltimore is a very artsy town. And so if you ever have a chance to come out and visit us at Space Telescope, we can give you tons of museum recommendations. And I'm sure there would be a ton of people who would be very happy to talk to you. So thank you again for having me, and I'll be happy to take questions.
Thank you. So questions, yeah, Shojit.
I have two questions. One is, how many computational resources do you need to produce the ray tracing Lyman alpha simulation? The other is, since you can have less delicate ray tracing simulation for Lyman alpha light, would you think that it is possible to expand it to other emission ones?
Yes, so Sukjan's models, he has also developed them to be able to look at H alpha and at nitrogen 5. And so that's something that we would really be interested in looking at. H alpha can also scatter. Nitrogen 5, we don't expect to scatter as much. And so we were really interested in Lyman alpha because of the implications that it has for chemistry. But we can definitely expand it to other emission lines. And then the first question was that how many simulations you need to run it. So if you ask Sukjan, he'll just say one. But we ran simulations to test a few different physical parameters. And so we ran, I think, 6 or 7 different simulations at different wind opening angles, ranging from, very small to wider. Then we ran simulations where we varied the size of the hydrogen in the disk. So we had it going from very small to all the way across the extent of the submillimeter disk that was observed with ALMA. And so I think that was probably another 4 or 5 simulations.
Or how many CPU hours you need?
Oh, that's a good question.
The ray tracing, even if you have a lot of scattering, it will be distant.
Yeah, I will ask him how many hours it used. Yeah.
Thank you.
Yeah.
Other questions? Dave?
Beautiful talk. Thank you very much. So you mentioned this before. This is something I actually thought about a lot. As somebody who kind of romanticizes and some of these astronomy observatories. So like the UV stuff with Hubble is on its way out. So you clearly here have an absolutely beautiful sample of things, at least in the protoplanetary regime of astronomy. You guys, now that you're going to get some all the data, I'm wondering, have you guys thought about, trying to use some of these data products that you have to, look for some UV tracers or something like that, basically try to come up with things for posterity, because like you said, I mean, after whatever Hubble gets cooked, I don't know, it'd be like at least 1 or 2 decades until we have a proper UV observatory again. So to me, this just looks like a really promising data set to maybe try to dig a little deeper and try to find some like nifty tricks for astronomers to use. So I'm just curious basically what your thoughts are on that.
Absolutely. So over time, the wavelength solution for the cosmic origin spectrograph has improved. And that's excellent work that's been done by the COS team at STSCI. And so as that wavelength solution has improved, it means that we're more able to look for kinematic signatures that we wouldn't have been able to see before. And so there's a grad student in Colorado now who is trying to look for kinematic signatures in H2 emission lines that we see in the UV. So these are Lyman alpha pumped electronically excited transitions of H2. And in spectral imaging of brighter sources, one bright source, we've seen these H2 emission lines chasing an outflow. And so we think in the disks that there are probably some wind signatures in there. And so this grad student is trying to untangle some of those wind signatures. So that's one thing. Another thing that we're trying to do is basically pad the mass ends of the low mass stars with ULLYSES. And so most of the targets in the low mass star category were K and M type T-Tauri stars. But there are some people that are trying to push for adding some brown dwarfs and substellar companions, because those are regimes that we're very interested in how accretion proceeds. And then in terms of thinking about the slightly higher mass Herbig stars, we don't have a lot of those that are included in the program as well. And so that's something that people are trying to push for while we're in this process of kind of wrapping up the ULLYSES survey. Yeah, but there's a ton to be done with this data, right? People are still working on understanding the flaring rates of young stars. We still have a lot of work to characterize some of the other stuff that will influence the chemistry. Then we can feed all of those measurements that we get from the spectra into thermochemical models. There's a ton of work to do. We might be pretty busy before Habitable World launches, honestly. So.
Yeah. Well, even with like the kinematics, I mean, with ALMA, you should also be able to get some kinematics as well. So that would be very interesting to see if, you know, to what extent those agree or disagree.
Yeah. So the thing is that the temperature of the molecules that we would observe with ALMA is very different. Mm-hmm. And so the winds that we're seeing, what we're seeing is warm gas that's being blown off of the surface layer of the disk. And the gas that we're observing with ALMA is slightly deeper. So that's not the stuff that's initially going to get blown out of the system. And so for the protostars and for the younger systems that still have a lot of material that's falling onto the disk, absolutely ALMA is great for tracing those envelopes. But for the more evolved systems, we really want to look more in the infrared and the UV to trace what's being driven out.
Do we have any questions on Zoom?
I don't see any hands, but if anybody has any questions on Zoom, now's your chance.
Okay, we'll go to Charles.
I have a very naive question about Lyman alpha spectroscopy. So I would think that there ought to be something carved out of your spectra corresponding to the local interstellar medium. How wide is that band where you just can't see anything?
Yes, that is an excellent question. So it depends on the system. So unfortunately, okay, so this is the multi-part answer. So the other reason why TW-HIA was targeted for this spectral imaging survey is because the line of sight interstellar extinction is very, very low. And so what we're seeing in absorption is effectively all circumstellar extinction. With the other targets that were observed with COS, the line of sight absorption is narrower than the geocoronal emission along the line of sight to the nearest star forming region. So we're not looking in directions that are very heavily extincted. And so the geocoronal emission is found between plus or minus 250 kilometers per second, and the interstellar absorption will fall inside there.
I actually have two questions. One of them would be on the slides where there were jets and no jets. Yes, so I'm just a freshman right now. I don't have the physics background and all of this. Could there be a relation between the planets and the jets here? Because depending on the type of star, it could just be blowing away the material for the planet formation.
This is an excellent question. So this is work that actually Carlo Manara and Justin Campbell-White are doing at ESO in Germany. So you'll notice that there's a little planet question mark here. So it's very, very difficult to directly detect planets in this disk, in any of these disks. We really only have one system with unambiguous detections, and that system is called PDS-70. So there are two little planets that have been beautifully imaged in that disk. And in the PDS-70 system, there was a nice paper that Justin led that found signs of a beautiful wind that's being driven out from the inner regions of this disk. And so it's quite possible that the wind is what actually contributed to the clearing of material that then let us see the planets. But, sorry.
So it could be that that has planets there, we just can't see it.
Exactly, yeah, yeah.
Thank you. And second question would be, it was before the slide where you were discussing the 71 new observations into the database.
Yes.
Yeah, the last slide before this.
This one?
Yeah, so the graph you're seeing here, you were talking about how it's a little different. Shouldn't it actually be like this? Because since this is a young star, it hasn't really entered the PMS phase right now. Sorry, the main sequence phase. So shouldn't it be chaotic and like just like this instead of
a black body?
Yeah.
Yeah. So the I don't know if well, maybe I can draw this. So with the young stars, we think that there should be a normal stellar you see this?
Yes.
Okay, a normal stellar SED, and then because there's so much extra UV radiation being generated, there should be an extra like blobby thing over here. But it's very hard to consider all of the emission lines that are added to this. And so if you were to just fit a really simple model to this, it probably would look something like a black body. But what we're seeing is that if you just use a black body in the models, it doesn't quite match what we're seeing in the observations. There's a little bit more complicated stuff going on. And so something that we can consider now that we have all of these beautiful UV observations are more realistic. We can just put the observations in, right? Instead of using an approximation.
That makes sense because it felt natural because of how young the star is. It might.
Yeah.
It made sense.
Yeah. There's a lot going on. So,
Exactly.
yeah.
Thank you.
So if I could ask a question, and we go back to the cartoon with the jet. So I used to believe, or at least I thought I had been told that the jet itself might be driven by disk wind. So when you have a disk wind but no jet, is that because there's this gap in the center, or what's absent that doesn't lead to a jet?
Yeah. So what we think is happening is that the mechanism that's driving the wind is changing over time. So in a state where we have a very optically thick inner disk, then we think that we're more likely to see MHD driven winds and then magnetically driven jets as well. And then once we have a cavity that's carved out in the dust, it seems like it's less efficient to drive those MHD winds and those jets, but photoevaporative winds can still be driven from the cavity here. And so you can have X-ray or EUV photons that are heating the material and letting it escape photoevaporatively. We don't really know yet why some of these disks don't show signatures of jets. This is work that Ilaria Pascucci has been doing for a while, but when you look at the semi-forbidden emission lines, or the forbidden emission lines from neon 2 and oxygen 1, you don't see any of the faster, the high velocity emission that you would associate with the jets, but we're not really sure what would turn them off.
Very interesting. Any other questions? All right, well, let's thank Nicole again. Thanks. And yeah, people are interested in dinner and congregate up here.